Welcome to this introduction to text encoding. And in this video, we are going to look at how computers store text on the file level. And this is what we're going to do. So first, we're going to have a look at some preliminaries. That is how do files work. And then we have a quick look into number systems. It's going to be a little bit of math, but nothing too serious. We are then going to look at the older standard, American Standard Code for Information Interchange, and the ANSI standard, and then we're going to look at Unicode. And finally, we are going to discuss why we care about this, or why this is important to us. So let's have a look at how computers store files. And at the very bottom here, we have the file system. And the file system controls how data is stored and retrieved on your computer. There are different types of file systems, but we're not going to have a look at that in this video. On top of that, we have files. And a file is essentially just a container for numbers. And usually these files contain bytes. A byte is a sequence of 8 bits, and a bit is either a 0 or a 1, basically a switch. And bits are what your computer is basically using for everything. So these are electrical signals, either 0 or 1. On top of the file, we have the encoding, or the file type. And this is what we're going to talk in this video particularly. And these are, so to speak, the rules for how to interpret these bytes. So basically, you have a file, and that is just a sequence of numbers, a sequence of bytes. And now we need to have some sort of rule set for interpreting these arbitrary or non-arbitrary numbers. And so, for example, if we look at plain text encoded in ASCII, we're going to look at that in a second. There are certain rules of what these numbers mean. And this is what the encoding is, or what the file type is. You've maybe encountered file endings, so that your file name ends in, for example, .txt, indicating the file type. This file ending, or this extension, doesn't really change anything about the file itself. It just is an indicator of how the bytes in that file are actually arranged, so that your computer then knows which set of rules basically to apply to understand the content of that file. And now on top of this, we could also have some sort of a format or markup. So for example, we have a file that is encoded in ASCII, and it contains plain text, so just characters. And now we could have some sort of additional markup, for example, XML or Markdown, on top of that file type that then carries some additional meaning. But for this particular video, we're going to look at this third layer here in the encoding of the file type. Because if we make mistakes here, especially if we work with textual linguistic data, we can get into some serious problems here. So that's what we're going to look at. In order to do this, we have to understand a little bit about number systems. And now don't worry, this isn't going to be crazy, but we have to look at a little bit of the fundamentals of how computers deal with numbers. So if we think about numbers, there are different ways of how we could represent them. Humans, at least most of them, we are most used to the base 10 or the decimal system. Probably because we have like 10 fingers and it's easy to count. Most number systems have place value. And now this will make more sense giving you this example. So in the decimal system, and that's just the system you're used to, this is regular numbers. So the number 234. In that number, we have 4 ones, we have 3 tens, and we have 2 hundreds, right? And if you were to write this out, 234, that makes a lot of sense. And if you remember back to how you do multiplication, for example, then you certainly remember that these places have importance here. So in the base 10 or decimal system, we have 10 symbols, basically 0 to 9. And whenever we move to the left, so to speak, we think in bundles of 10. So if we move from 9 to 10, we move 1 to the left. And then we have 0 ones and 1 10 and 0 hundreds, for example. And if we express this in terms of powers, then 10 would be 10 to the power of 1, 100 would be 10 to the power of 2, and so on and so forth. Now, there are different systems to that. And while the decimal system works quite well for humans, the binary system works extremely well for computers. And in the binary system, we have 2 symbols, and that is 0 and 1 bits. And the places here are powers of 2, essentially. So if we have a look at this, we have, in this example, we have 8 places. So we have 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 2 to the power of 5, 2 to the power of 6, and 2 to the power of 7. And now if we want to basically write a number in binary, we are basically placing 1s or 0s in these places. So let's say we wanted to express the decimal number 234 in binary format. So we can have a look at this. So we need 128. That's 2 to the power of 7. So we take that. Then we also take the 64. We can add these, so that's a 1. We also take the 32. It's also 1. We don't take the 16, but we take the 8. We don't take the 4, and we take the 2. And if you add these up, that will add up to 234. And that gives you the sequence of 111, 01, 010. And that just corresponds to these places in the binary table down here, in the binary system. So if we look at these side by side, basically, while you would have in the base 10 decimal system, you would have 1s, 10s, and 100s. Here you have 1s, 2s, 4s, 8s, 16s, and so on and so forth. But of course, you can only ever have either one of those or none of those. So the plural form here doesn't make too much sense, actually. So that's the internal representation of your computer's number system. Now, there's an additional one, and that's the one most interesting to us for that video, and that is the hexadecimal system. And in the hexadecimal system, we have 16 symbols. So we have 0 to 9, and then we also have A, B, C, D, E, F. So A would basically represent a decimal 10, B would represent a decimal 11, and so on and so forth. Now, why do we do that? Well, given more symbols, we need less places to represent a quantity. So we have a higher information density. We're going to look at that in a second. Also, hexadecimal is just easier to read than binary. So let's look at the table again. So in decimal, we have 1s, 10s, and 100s. And here we have 1s, 16s, and 256s, so to speak. And now we have 16 symbols we can put here. Remember, in binary we had 2, 0, and 1. In decimal we had 10. Here we have 16. So if we want to represent the same number here, so 234, we would place EA, so it's EA hex. That is on the 1s, we place an A, and the A is basically 10. And on the 16th position, or the 16th place, we put an E. And an E is 14. So it would be 14 times 16 plus 10 times 1. And that is 234. And that is how we can represent these numbers in hex. And now you can see what I mean by information density. So to express this number in binary, we would need quite a significant number of characters. To be precise, 8, a whole byte. Now in decimal, we would need, or we need 3 characters, 2, 3, and 4. And in base 16, we only need 2, E and A, right? So that is very efficient in terms of information density, and is also easier to read than binary. So whenever we look at files, we usually, at least if we do this with a computer, we will usually see hex values. And since we will see a couple of these, I just wanted to show you these so that you don't get confused. I know this is a lot, but you don't have to understand this fully. Just be aware of this, that this exists. All right, let's go into the actual topic here, and that is encoding. So computers, as we've seen, can only store information as numbers. And so in 1963, the first encoding standard for text was published. And it is called the American Standard Code for Information Interchange, or ASCII. And in ASCII, it's quite simple. So you have 128 characters. 32 of these are non-printable control characters, but the rest is actual printable characters. And each of these characters is represented by a number between 0 and 127 decimal, or the corresponding values in binary or hexadecimal. Now, since 127 is smaller than 128, we only need 7 bits to represent a character. So in an ASCII encoded file, you would find basically multiple 7-bit strings, each of these 7 bits representing one character. Now, since a byte has 8 bits, there was 1 bit left, kind of. Files are written in bytes, so using ASCII, we always had 1 bit more than we actually needed. And quickly enough, people started to use that additional bit to come up with custom encoding schemes and custom ways of representing text and characters. And that was very much needed because the ASCII standard basically only contains the Latin alphabet, Arabic numbers, and a couple of punctuation symbols, more or less. And of course, there's way more than that. And so people use that additional bit to represent other more complex, or not necessarily more complex, but just other writing systems. And so what emerged out of this is just a myriad of different standards or ideas of representing data, and it was just pure chaos. Now, in order to combat that, a little bit later, we got the so-called ANSI standard. And it's not really a standard, it's just more of a colloquial term used to describe a variety of standards. But what all of these standards have in common is that they have strictly an 8-bit representation. And this can be seen as an extension of the ASCII character set. And whenever we encounter ASCII files today, they are usually actually ANSI files. We're going to look at this in a second. So, for example, a very common one is the Latin 1 standard. And so if you hear the term ANSI, what is actually meant often is the Latin 1 standard. Now, this was a whole lot of theory. Let's have a look at what this looks in practice. So here we see the inside of an ASCII encoded text file. And to the left here, you basically see the view of a so-called hex editor. And the hex editor shows us just the raw content of a computer file. Not the interpretation, but just the raw content. Well, to the right here we have decoded text. So the text editor I'm using actually shows you, or attempts to decode that, but this is basically what's in the file. So this particular file contains ABC123, and we can see here that this is 6 bytes, 1 byte per character, as defined in the ASCII standard. And here to the right, we can see part of the ASCII chart that basically gives us the correspondences of numbers and characters or glyphs. So in the ASCII standard, the decimal 65 or hex 41 represents an A, hex 42 is B, and hex 43 is C. And basically in the file, there are just these numbers, and then your computer basically takes this ASCII chart and translates these numbers into characters. Now we can go even further and do this ourselves basically, or type text straight in hex and see how that works. So this here is HXD, it's an hex editor, and I'm writing a new file here. And so now I'm writing in hex. So we're going 48. 48 is an H, 65 in hex is an E, 6C is an L, another 6C, that's again an L, and then 6F is an O. So this is just a representation of hello. And if I'm now saving this file as a TXT, and then we can just see what's in there. All right, so I've just opened that file and it reads hello. And this is now an ASCII or ANSI encoded text file. All right, so this is ASCII and ANSI. Very straightforward. You just have numbers, and then you have a table, and you look up what character is represented by this number. It's a very straightforward system, worked quite well. However, given the situation with ANSI and the multitude of different standards, that's just a pain. And it still is a pain because these are still used from time to time. Therefore, we came up with Unicode. And the idea behind Unicode is to have a single character set. And a character set describes this kind of table here that includes every writing system, or more or less every writing system. Now, Unicode is a whole lot more complex than ASCII or ANSI because characters aren't directly mapped to numbers straightforwardly. But first of all, they are mapped to so-called code points. And a code point, so for example, U plus 0041, which is an A, that is an index, again, in a table. That works very similarly to ASCII or ANSI. So you have this large table, and we're going to have a look at this, containing these code points indicating which character is represented by this. However, you can't just type these code points in a file and it'll work out of the box. And we'll see why that is in a second. Overall, in Unicode version 13, as of March 2020, there are over 140,000 different characters. Now, as I said, we can't just type these code points into a file and expect it to work. And that is because these code points, which are essentially just numbers, they need to be encoded. So while in ASCII, the whole encoding process basically is just looking up this in a table, writing it into a file. With Unicode, there is an extra step. So we have to look up we have to know the code point, so to speak. And then we need to encode that code point into a representation that we can put into the file. Now, the most common representation, the most common encoding used now is UTF-8. Now, it's important to not make the mistake to say that UTF-8 is Unicode. Unicode is a standard, and Unicode is more or less this collection of tables containing all of these characters and their representative code points. And now, there are various encoding standards used to put this information into files. So UTF-8 is a way of encoding Unicode characters. So what does this look like? So this is part of the Unicode charts, so to speak. This is the chart for Arabic, and this is the range 0600 to 06FF. And for example, we can see here that the character ba, which has the Unicode code 0628, can be represented in the UTF-8 encoding as D8A8, or in UTF-32. That's another type of encoding as 0000000628. Now, the interesting bit here is that UTF-32 encodes characters as 4 bytes, and there's a clear link to the code, so the code is just represented in here. Well, UTF-8 works a little bit differently. But that's essentially what it is. So we have a code, and then we have an encoding standard to put that code into a file. So UTF-8 uses 1 to 4 1-byte 8-bit units. And as I said, in comparison, UTF-32 uses always 4 bytes. Now, the cool thing about UTF-8 is that it is backwards compatible with ASCII. So basically, in UTF-8, it's the same encodings than it is in ASCII. So for example, for the capital B, we have the Unicode code 0042, and in UTF-8, that's just a hex 42. And in UTF-32, it's basically the same thing, but it's on the last byte here. And if we remember, 42 basically was the B in ASCII. Now, of course, in UTF-8, there are many other characters, not just the ones that are in ASCII. So for example, the small sigma here, the code would be 03C3 in hex. In UTF-8, it's CF83, and in UTF-32, it's 000003C3. So we can see in UTF-32, we have a clear representation here, and it's basically 2 bytes here at the end. Now, it's important to note that we can't just add up the UTF-8 bytes to get to the code. There is a bit of a more complex process here that I'm not going to detail here. Just be aware that it exists. It's not necessarily hard, it's just a little bit of more math. But basically, UTF-8 is a fairly compact variant of encoding codes, right? And UTF-32, which is often used internally, is a easier to read, more direct representation of the code. But of course, since it uses always 4 bytes, it takes up a lot more space. Now, what does a UTF-8 file look inside? So this is a UTF-8 encoded text file, and this contains ABC and a heart. And now we see a lot here. So the first 3 bytes here, EF, BB, BF, that is the so-called byte order mask. And that is just 3 bytes in front of any Unicode text that basically signals this is Unicode. What now follows is Unicode. Now, this is part of the standard, but sometimes this is omitted if we can expect the computer or the software to know that it's Unicode. But this is an indicator that this is now Unicode. Now the A, B, and C are represented using 1 byte, A, B, and C, and that's totally compatible with ASCII. And then lastly, we have the white heart, and the white heart is represented as 3 bytes in UTF-8, and it is the code 2661. And that demonstrates the fact that in UTF-8, we can use anywhere between 1 and 4 bytes to represent or to encode 1 character. And that's important to note. Now, Unicode, of course, also has support for emojis, at least since version 6. So for example, the bear face emoji, that is Unicode 1F43B, could be represented in UTF-8 as F09F90BB, and it's always 4 bytes. Now, side note here, the representation of an emoji is up to the software, basically visualizing the emoji. So you can think of an emoji just like as of a font. So on different platforms, emoji will look different. And it's not actually specified what they particularly look like in the standard. And so here's 4 examples of what the bear face emoji could look like. But for our intents and purposes, an emoji is just another character and is represented as 4 bytes in UTF-8. Now, all of this has implications for file size. So in UTF-8, due to the variable length, 1 to 4 bytes, file sizes work differently to ASCII. So in ASCII, or let's say in ANSI, 1 character is 8 bits. It's 1 byte. So if we have a text of 1,000 characters, we know exactly what the file size is. Now in UTF-8, since we have variable length, it's not as easy. So here are 3 examples. So we have ABC. That's straightforward. That's 6 bytes. It's 3 bytes for the bomb plus 3 bytes for A, B, and C. And the bomb being the marker for that it's Unicode. Now, if we have ABC and the letter U, sorry for the pronunciation, U, we have 3 bytes for the bomb plus 3 bytes for A, B, and C, and now 2 bytes for the additional character. If we have this last example, A, B, and C, and then the same thing, but we add another emoji. Emojis have 4 bytes, we get a total of 12 bytes. So if we want to estimate the file size, for example, of a corpus, it's not as straightforward as with ASCII, but we have to make certain assumptions of what types of characters are in there. Now, if we look at the UTF-8 standard from a space perspective, we can see that this is clearly optimized for the characters in ASCII. So since ASCII is basically represented as 1 byte, ASCII characters can be stored with lots of space efficiency. Now, while this is nice for the English-speaking community, so to speak, of course, this has implications for other languages. And if we wanted to discuss this, we could also think about whether this is a good thing or whether there could be alternatives to that, since UTF-8, from this perspective, is kind of favoring Latin scripts, right? So that's something that could be discussed. Okay, so finally, why do we care about all of this? Well, first of all, to this day, although Unicode is quite old, not all tools understand Unicode. So sometimes you will just run into issues. If you are lucky, you will just see, well, kind of weird-looking characters because the tool just doesn't understand Unicode and it will just show you some sort of approximation. However, if you are unlucky, the tool will just basically not display the letters or the characters at all, and it will just basically put them into the garbage bin, and it will just show you the ones that it can actually read, and that's usually just what's in ASCII or ANSI. So be very careful to not basically miss out on some data if you use tools that don't support Unicode. We've just talked about the fact that sometimes we need to estimate space or storage requirements, especially if we are working with big data, and we have to be aware of how the data is encoded to do that. Sometimes we encounter issues when storing data. So for example, with MySQL databases, it's a very specific case, but it's an interesting one. The default settings for UTF-8 in MySQL only stores up to 3 bytes. So if you've set your database to UTF-8, you won't be able to store emojis, right? If you wanted to store emojis, you would have to set your MySQL database to UTF-8 MB4. And you just have to know this, because if you don't do this, you either lose out on the emojis or it just doesn't work at all. So we have to be very aware of what we are storing and how we are storing this. Now, sometimes we also want to convert between encodings. So maybe you got something in a strange esoteric encoding, and you want to take this and put it into your database, and you want to encode this in UTF-8, or you get something in UTF-8 and you want to do something else with it. We need to be very careful to convert correctly, because otherwise it can happen that we carry along basically broken characters without realizing it. And as long as we have the original data, that's not a problem. But if we don't have the original data anymore, or if we extract this from some other system and something goes wrong, we could lose valuable information in the process. Now, of course, this is also very important if we are looking at internationalization and different writing systems. And if we want to, for example, have multilingual data, we need to find ways of representing these other writing systems. It's also interesting from the perspective of the complexity of characters and just the sheer amount of characters. So as we see in the Unicode, there are over 140,000 characters. So that gives you kind of the perspective on how many characters there are and how much needs to go into this. And finally, I want to point out that Unicode also has this very nice side effect, not necessarily a side effect, I mean, it's in their mission statement, that everyone should be able to use their writing system, especially on all their devices. So Unicode allows people to use their preferred writing system, while before having just ASCII or ANSI, people had to basically resort to Latin characters to somehow encode their own writing system. And nowadays, having Unicode, people can just produce digitally their own writing system. And that's just a very cool thing to have. So that concludes this introduction to encoding. I know that this is quite a bit of complex material and that we've covered a whole lot, but hopefully this gives you a basic understanding. And the bottom line is always use Unicode and just be very aware of the fact that text can be stored in very different ways, and that this could have implications for storing and retrieving and analyzing data